All right. Almost the end of February. Hope everyone's, I guess, fully into the swing of the semester. I wanna, oh, yes. Possibly, but like, don't arrange things so that you're really counting on it. I'll try to, but not a firm promise. Good question though. Good. Other sort of bookkeeping things before we dive in to the material? Okay. So we've been spending a lot of time thinking about how and if people playing in a game might reach equilibrium, and towards that end, we've defined a whole bunch of different kinds of equilibrium. Right, so we're just coming off of a lecture where we basically explicitly defined this, larger class of equilibria, correlated equilibria, so that we would have a story that people, converge to equilibria in general games. Okay, so that's all well and good. Maybe we've made some progress towards establishing that the following kind of prediction, has some, reasonable grounding, which is that, in many classes of games, at least in the long run, people will end up playing at or near some equilibrium of some sort. But, like, that's not like a super crisp prediction, in that even if it's true, there might be many different equilibrium states, right? Like even in really simple games, and even when we like restrict attention to things like pure strategy and Nash equilibria, right? We saw really early on that games can very naturally have more than one pure strategy equilibrium. And of course, as we've expanded the scope of what we consider an equilibrium, as we move from pure strategy Nash equilibrium to mixed strategy Nash equilibrium to correlated equilibrium to coarse correlated equilibrium, we're only making this multiplicity problem worse, right? Because at every step of the way along this sort of hierarchy of generalization, we're keeping all of the old equilibrium and we're adding new ones, right? So like in doing this, in expanding, up to correlated equilibrium, we've maybe made the prediction that we will end up at some correlated equilibrium, at least oftentimes in the long run, plausible. But we've also weakened the prediction in that, like, we might be predicting that the thing that is going to happen is just one thing in a collection of things that might be really big, might be a lot of equilibria, right? So sort of the sharpness of our predictions has kind of degraded. And so what I want to think about in this class is sort of a way in which we might nevertheless be able to make sharp predictions about something. Not necessarily at the level of what action or what distribution of actions will every player play. Like, that's going to be tricky because, we know there's lots of different, even pure strategy Nash equilibria generically. But maybe the thing that we care about is not specifically, what action is player 1 going to play, and what action is player 2 going to play, and what action is player 3 going to play. Maybe the thing we care about is something, some sort of higher level summary of behavior, like what will the social welfare be, right? Like, if what I care about is like the sum of player costs or utilities, maybe I can never, like maybe even though I can't predict exactly what everyone's going to do because there's lots of equilibria, for example, maybe I can nevertheless say something about what the social welfare is going to be, that it will be, at least this big and, never more than that, something like that. Okay, so that's sort of going to be like what we try to do in this game. We sort of take as a given the presumption that play in some game will converge to an equilibrium, okay, of some sort. In this class, we'll think about Nash equilibria, but you could go through the same exercise for correlated equilibria. But without assuming we know which equilibrium will converge to, and then we'll try to figure something out on the basis of that prediction. Assuming we're going to converge to equilibrium, what can we say about, the social welfare of the game, the sum player costs, for example? Is it going to be good? Is it going to be bad? Okay, and in particular, we're going to define two quantities that are called the price of anarchy and the price of stability, which are what you can think of as the pessimistic and the optimistic answer to this question, respectively. Okay, so if I take as a premise that the kind of play I'm going to observe will be some equilibrium, but there might be many equilibria, the price of anarchy sort of asks the question, what's the worst case? How bad could things get in equilibrium? Meaning, we're sort of going to study the social welfare at the worst Nash equilibrium, like the worst possible Nash equilibrium for social welfare. And we'll talk a little bit about where these names come from, but like informally, if the premise is really, I have no control at all over what people do, I just think that for the kinds of reasons we've been talking about in this class, it'll end up at equilibrium. The only kind of robust prediction I can make, unless I have some theory for how people choose amongst equilibria, is that things will be no worse than the worst possible Nash equilibrium. And that's sort of the price of anarchy. On the other hand, if I have some ability to nudge people, like maybe I'm rolling out some app and I can't force what people are going to do, but I can set defaults maybe, right? Maybe I can sort of set things going at some initial state and then people are going to be free to deviate, then maybe I can't hope to implement behavior that's not at equilibrium because people will eventually figure that out and deviate away from it. But maybe I could, set the initial preferences or whatever in the app so that things are at equilibrium. And maybe if I do that, I sort of expect play to be stable. Nobody has any reason to deviate. And if I had that power, then I could arrange things so that the initial state of the game was not at just an arbitrary equilibrium, but at the best equilibrium. Okay, and so the price of stability asks, okay, like, if I don't have the ability to force people's actions, but I can set the initial state of the game, how good can I make things? What is the social welfare at like the best equilibrium? And it's called the price of stability because, the only reason I can't just set things up at like the socially optimal state is because that's not a stable solution. People will deviate away from it if they can beneficially do so. And like the price of stability asks, okay, like if people have the ability to deviate away, and so I need to find a stable state in this sort of game theoretic setting, but otherwise I can pick any stable state. It's asking like, what is the cost of that compared to optimal? Okay. And so in this class, we're going to ask all of these questions. It's sort of like a case study. We're going to go through how you can ask and answer these questions for Nash equilibrium. But in general, this is, you can imagine going through this exercise for any class of equilibria, right? For correlated equilibria, for coarse correlated equilibria, whatever you think is sort of a computationally plausible prediction in your setting. Okay, that's the game plan for today. Any high-level questions? Okay, so like if we're going to talk about how bad things could get and how bad things must get, we need to, right, like implicit, this is something that sort of never came up when we were just talking about game dynamics, because the individuals, they're just optimizing their utility function. But now we're sort of talking about, a judgment call. What is the thing that we as like the, designer care about and are optimizing when we're asking for, how good things are, how bad things are. We need to fix like what is the thing we care about, and that's going to be encoded in an objective function. Okay, so in general, and you could talk about this with utility functions or cost functions, I'm going to be talking about a class of congestion games today. So players are going to have cost functions rather than utility functions. And the objective could in principle be anything. It's just, some function that maps game states to real numbers and specifies, like, how good or bad each game state is. And in this, again, like just as you could study the price of anarchy or the price of stability for any objective function, just to make things concrete, since we have only one lecture on this topic, today, the objective function that I'm always going to be talking about is what's called social welfare, or in this case, social cost. Okay, and it's just like a utilitarian objective. It is what is the sum or average cost across all of the players in the game. Okay, so just to, so in principle, you could talk about any objective function. We're going to talk about social cost, which is a natural one. And because we're talking about cost functions rather than utility functions, we would like social cost to be small. We'd like to sort of minimize people's average cost. But of course, if we were talking about games that had utility functions, social welfare would be the sum of the utility functions, and we would want that to be big. Okay, but this is just a normalization thing. Okay, so the point is, like from the point of view of this lecture, we're always going to be talking about Nash equilibria. We're always going to evaluate the quality of an equilibrium by the social cost, the sum of players' cost functions. But you should keep in the back of your mind that this is really just an exemplar, and you can talk about the price of anarchy or the price of stability with respect to any class of equilibria and with respect to any objective function. Okay. So now we can define the price of anarchy and the price of stability. And so, we want to talk about how good or bad different equilibrium game states are in terms of our objective function, in terms of social cost. And the question, one of the first questions you should ask is, compared to what? Okay, so the benchmark we are always going to use here is what I will call opt, which is sort of like, the optimal social cost you could arrange if you didn't have to worry about incentives, if people would just do what they were told, or if there were no people, if it was just, an algorithmic problem you were solving for. Okay, so opt is just the minimal possible value of the objective function, right? Like if you, like in a traffic routing game, for example, this would be sort of the minimum average commute time. If I could direct everyone's car to go where I want it to for the sole purpose of minimizing average commute time, and I didn't have to worry about whether for every particular person, the route they were taking was the minimum cost route for them. Okay, so in particular, like the game profile, the action profile that optimizes social cost might not be a Nash equilibrium. This is sort of the source of the tension here. Okay, so like opt is something that would be like achievable if you had global dictatorial control and could just optimize for this objective function, but it might not be achievable in a game theoretic setting, because we've seen plenty of examples where, with things as simple as prisoner's dilemma, where equilibrium is just sort of, at odds with the outcome that sort of globally maximizes people's utility. Okay, but nevertheless, that's going to be our objective. Does that make sense? That's going to be our benchmark. Okay. Okay, so that's opt. Like if we didn't have to worry about people making individual decisions, we would just compute opt and we'd tell them to play that. But like since we're talking about a strategic interaction, that's not what's going to happen. People are going to make decisions to optimize their own utility functions unilaterally. I'll change my action if it makes things better for me, even if it makes things worse globally. And so informally, the price of anarchy measures how much worse the objective, in this case, the social cost, could be if I assume that players play according to a Nash equilibrium, but I assume nothing else. So in particular, like they might play according to the worst Nash equilibrium, the Nash equilibrium that has the worst social cost. And the units in which we will measure the price of anarchy are sort of in comparison to opt. How much worse is the social cost multiplicatively compared to opt? Okay, so in particular, the price of anarchy of some game G is the worst case, the maximum, over all Nash equilibria of the game of the ratio of the social cost at that Nash equilibrium compared to opt. So for example, you know, like if the only Nash equilibrium actually is the game state that minimizes social cost, then the price of anarchy is 1. That's like the best case. But if there's an equilibrium such that the social cost is twice as bad as opt, the price of anarchy is 2. Okay, it might not be terrible. If there's an equilibrium, say it's an n-player game, if there's an equilibrium where the social cost is like n times as much as opt, where n is the number of players, the price of anarchy would be n. And that would be pretty bad. It would mean that the, sort of the, you know, how bad things can get as a multiplicative factor of opt can sort of, you know, there's no limits. They can, you know, as the game gets bigger, they can get arbitrarily bad. Okay, but that's what the price of anarchy is measuring. The questions about the definition, we've in general to talk about price of anarchy or price of stability that we'll see in a moment, you need to pin down a class of equilibrium solution concepts that you're going to maximize over. In this case, we're talking about Nash equilibria. You need to pin down an objective function. In this case, we're talking about social cost. And it's just the ratio between how bad things can get in the worst equilibrium as measured by your objective function compared to opt. By the way, this is something you'll encounter on the homework. When we talk about the price of anarchy, it's sort of natural that it be a number bigger than 1, right? So sort of 1 is like the best case, but like if things can be twice as bad as opt, the price of anarchy is 2. If things can be 3 times as bad as opt, the price of anarchy is 3. And so if we were talking about a game with like utility functions where we wanted to maximize social welfare rather than minimize social costs, the natural way to define price of anarchy would be to take the reciprocal of this, so that the price of anarchy would still be a number that was 1 or larger. Okay. Okay, good. So any questions? Okay, so the price of anarchy is like this pessimistic measure, which is sort of natural from a computer science perspective, right? We're sort of used to worst case analyses. And on the one hand, those are nice because they're robust. If we're not making assumptions, in this case, about which equilibria we might converge to, then, you know, like we're not going to be wrong. Like, you know, as long as we converge to some equilibrium, it's not going to be worse than the worst one. But on the other hand, like, a pessimistic analysis might not be appropriate in every situation, especially if we are in a situation where, for example, by setting the defaults on some app, I'm in a position to sort of nudge people in the right direction, sort of pick the initial state and have the presumption that so long as I've picked an equilibrium, so long as the initial state is stable in a strategic sense, I'll stay there. And so the price of stability is sort of the optimistic version of the price of anarchy, which again maybe makes the most sense in settings where you can actually pick the initial state. So, you know, the price of stability is also going to compare the ratio of our objective, in this case, social cost, at some equilibrium A compared to the optimal social cost. So again, it's going to, this price of stability, it's going to be a number that's bigger, you know, greater than or equal to 1. But rather than measuring this at the worst Nash equilibrium, the Nash equilibrium that maximizes social cost and therefore this ratio. We're going to measure this, if we're talking about the price of stability, at the best equilibrium, the equilibrium that minimizes social cost or this ratio. Okay, so very similar to the price of anarchy. We're measuring the same quantity, the ratio of our objective at some equilibrium compared to opt, but here we're measuring it at the best equilibrium rather than the worst equilibrium. Okay, makes sense. Okay, so like generally computer scientists are bad at naming things. Like if you've taken 262 or like a complexity theory class, there's P and NP, and you always have to like explain, NP does not stand for not polynomial time. It's like non-deterministic polynomial time. So okay, well, we're generally bad at coming up with names, but like I think in this case the names are sort of evocative. If the names should, if you sort of file this away in your brain correctly, the names should remind you of what the quantity is. Okay, so the price of anarchy is sort of, what happens if you have no control at all. People are just optimizing entirely for themselves, and you're unable to make any assumption at all other than they arrive at some equilibrium. The price of stability is sort of how bad things can get if you can tell people what to do, but like you're constrained to suggest, to tell them to do something that is stable in a game theoretic sense. Okay, so one other, question just to like check your understanding. So as I mentioned, I've just defined price of anarchy and price of stability over Nash equilibria, but it's very natural to define these things for, any of the solution concepts we've talked about: pure strategy, mixed strategy, correlated, coarse correlated equilibria, any of them. The definition would just change the set that we're optimizing over. It would be min and max, not over the set of Nash equilibria, but for example, over the set of correlated equilibria. Okay, so I claim that, if I looked at the price of anarchy in some game and ordered it over the solution concepts we've thought about, the price of anarchy for pure strategy Nash equilibria would be the smallest. The price of anarchy for mixed strategy Nash equilibria could only be bigger. The price of anarchy for correlated equilibria could only be bigger. The price of anarchy for coarse correlated equilibria could only be bigger. Can anyone tell me why this is the correct ordering?
Subsequent thing is like a subset of the.
Each subsequent, exactly, like.
The max of the whole pure strategy, then it has to be within the max.
That's right. It's because these solution concepts are nested within one another. A Nash equilibrium is a correlated equilibrium, is a coarse correlated equilibrium, and we're maximizing over the set. So if we're maximizing over a strictly larger set, we can only get a strictly larger value. What if I were to talk about the price of stability and to arrange these things? What would be the ordering? What does that mean? Yeah, so if it was the price of stability over coarse correlated equilibria would be the smallest, then correlated equilibria, then mixed strategy, then pure strategy, Nash equilibria. How come? Yeah, so it's because we're minimizing for the price of stability. So if I'm minimizing over a larger set, I can only find a smaller value. Okay. Okay. But we're going to talk about congestion games in this lecture. We know congestion games have pure strategy Nash equilibria. We have a computationally plausible story for convergence to pure strategy Nash equilibria, these best response dynamics. But we don't necessarily know which equilibrium we get convergence to. And so it makes sense to think about both price of anarchy and price of stability in congestion games. But it also makes sense to think about it over pure strategy Nash equilibria. For other games, we might want to enlarge the class. For now, we're going to talk about these concepts over pure strategy Nash equilibria. Okay. And so we're going to talk about the price of anarchy and price of stability for a variant of congestion games that sort of I mentioned when we talked about congestion games, but we didn't think about it in great detail, called fair cost sharing games. So maybe just to sort of remind you, okay, what is a congestion game, and then what is a fair cost sharing game? So remember, way back when, like upwards of like a month ago at this point, we talked about this class of congestion games, and what made congestion games special was that there was this set of objects called facilities, and an action, like an action for a person, was always a subset of those facilities. Okay, so at the time we were talking about like traffic routing games. The facilities were the roads in a road network. The action you could take is a path, like from your source to your destination. That's a subset of the facilities, and that involved some number of players like playing on each of the facilities, right? Like there's some number of people who play on this road, and each facility had some cost function, which for facility J we called LJ, and the cost of that facility was a function only of the number of people playing on it. We didn't care who was playing on it, just the number of people playing on it. So like the cost of facility J is the load on facility J when at action profile A and J of A people are playing on it. And your cost for playing some subset of the facilities was just the sum of the loads on the facilities that you played on. Okay, that was like the defining characteristic of a congestion game. And in traffic routing games, we had these, arbitrary loss functions, but like there was always the sort of, maybe implicit presumption that they were increasing. Like if we're modeling traffic on a road, like somehow the more cars are driving on the road, the more congested it should become, the longer it should take to drive along the road. In a cost sharing game, things are different. In a cost sharing game, it's still a congestion game. We've got facilities. Each facility has some loss function. You play on a subset of the facilities and experience cost equal to the sum of the load on the facilities you're playing on. But the loss function for a facility is now decreasing in the number of players playing on it. Okay, and the idea, just to sort of tell a story about these things, the idea is that what you're doing by playing on a facility is like building infrastructure. Okay, so think about like producing, like fiber optic network to connect different nodes in a network. Right, so maybe I've got a graph or something, and there's players who correspond to source destination pairs in this network. And what they would like to do is, buy or build, commission to be built fiber optic network to connect, their source and their destination pairs. Now, maybe different stretches of the network are, would have different construction costs, right? Like if I have to like tunnel through a mountain or something, it's going to be really expensive. And so each potential edge has some like just cost to build it. I'll call it WJ. But like, maybe you and I can share edges. So maybe, like we could all build our own disjoint paths connecting source and destination and not share anything. But if we did that, we'd have to, like produce this infrastructure on our own and pay for its entire cost. But if we can collaborate and find ways to share even some of the edges, then what happens is we split the cost to build it. Okay, so like the fiber optic network costs the same total amount to build no matter what. But the idea is if K people are going to share like an edge in this network, the cost for each of them is just a 1/K fraction of the total cost to build it. Okay, the idea is if we can share, capital expenditures, to build out this infrastructure, what's going to happen is we're just going to split the costs equally. Okay, so this is a congestion game. but it's a congestion game where the costs have this, like the costs of facilities have this particular form where there's some overall cost for building the facility, WJ, and that cost is split evenly across all of the players who use that facility. Okay, so it's just a congestion game where in particular the cost of a facility J has the form, some constant WJ divided by K, if K people are playing on it. Okay. Other questions about this class of games? Yeah. So let's see. So first of all, let's just remember how congestion games work. There's like a cost for each facility. Okay, that's what LJ of K is. This is like the cost for facility J if K people are using it. And then your cost in the game as a player, you're going to play on some subset of the facilities, some path in the graph, say. Your cost is the sum of the costs of the facilities you're playing on. Okay, so each facility J has this cost, WJ over K, if there's K people playing on it, and then your cost as player I at some particular action profile is the sum overall of the facilities you are playing on of the cost of that facility given how many other people are playing on it at that action profile. Good. Good question. Other questions? Okay, so this class of games make sense? It's a congestion game, but we're making a further assumption on what the cost functions look like. Yeah.
Before it was that cost could also decrease with an increase, right?
Say that again.
More people using it could decrease the overall cost.
Yeah, that's right. So this, in congestion games, we didn't we analyzed the convergence of best response dynamics in general congestion games, in which we made no assumptions at all about what this loss function looks like. But I think when we were talking about traffic routing games, it was natural to think about it as probably increasing. But you're right, we didn't assume that, and that's why we can talk now about cost sharing games in which these are decreasing, and everything we know about congestion games is still true. These are congestion games. Did that answer your question? Good. Other questions? Okay. Okay, so I think we said this already, the thing that this is modeling is just that, we're building, infrastructure that has some fixed capital cost, and that cost is going to be split uniformly across all of the players who are using each particular piece of infrastructure. Okay, and so one thing that is convenient to notice here is at some particular game state, what is the social cost? Well, social cost in general is the sum of the costs of all of the players. But we can think about that as, okay, each player, their cost is their cost summed across all of the facilities. So we can think about social cost by first summing over the facilities and then summing over the cost of each player for that facility, right? Because social cost is this double sum over the players, sum over the cost, sum over the facilities of the cost of that player at that facility. Now, the cost of each player at some facility J, if there's K players playing on it, is WJ over K, right? It's the capital cost of facility J split K ways. And if there's K people playing on it, then there's K people who are paying this cost, WJ split K ways. So what are they paying in aggregate? They're paying WJ, right? Which makes sense if you think about, splitting these capital costs equally, the sum total that people are paying is the sum total construction cost for all of the facilities. Okay, so in this case, if I look at the social cost objective, which is just the sum over everyone's individual cost functions, that is just the sum over all of the facilities that anyone plays on of WJ. It's the sum of the construction costs of all of the facilities that we end up building. Okay, it's this very simple thing. And it's because for every facility, there's exactly K people paying the cost of that facility over K. In aggregate, they're paying exactly the construction cost for that facility. Okay, so this is a useful thing to observe. So I just want to make sure people understand that. Okay, so is that clear? Like we're going to study the price of anarchy and price of stability in these games. We care about the social cost objective, but like the social cost objective, which generically is the sum of the cost functions of all of the n players, in this case simplifies out to just like the sum of the construction costs for all of the facilities that have anyone playing on them at all. Make sense? Okay. Okay, so let's start thinking about what is the price of anarchy and price of stability in these games. And let me, and there's like a definitional ambiguity here that I want to clear up first. So like when we talk about price of, and when we defined price of anarchy or price of stability, it's like, okay, for a particular game, we're gonna like maximize or minimize over all of the equilibrium of that game. It's clear what that means. Like there's a particular game, there's finitely many like game states. Each game state is or is not in equilibrium. We'll just take the maximum over all of the game states that are equilibrium. Okay, but like now I'm gonna like state a theorem that is talking about like the price of stability for fair cost sharing games. Or what does that mean? Like a fair cost sharing game, like fair cost sharing games are like a class of games, right? There's many different, I could write down many different fair cost sharing games that would differ in how many players there were, how many facilities there were, what these WJs are, right? Like there's many different things that would be instances of fair cost sharing games. So what do I mean when I talk about the price of anarchy or the price of stability for fair cost sharing games? Well, what I mean is I am going to consider, I'm going to quantify over all possible fair cost sharing games. So when I say that for fair cost sharing games, the price of stability is at least log n. What I mean is in this case, there exist fair cost sharing games for which the price of stability is at least log n. It's not true for every fair cost sharing game. I could write down a fair cost sharing game with one player and one facility, and clearly there wouldn't even be a game. Like there's only like one action. The price of anarchy and price of stability in that game would be 1. There's no decisions, right? So I don't mean in every fair cost sharing game the price of anarchy is log n. What I mean is for every n, there exists a fair cost sharing game whose price of stability is log n. Okay, so that's sort of a more formal statement of what this theorem is. Okay. Right. And okay, so with that in mind, the theorem I want to claim is that for the class of fair cost sharing games, the price of stability over pure strategy Nash equilibria is at least the nth harmonic number, which is just 1 plus 1/2 plus 1/3 plus 1/4 all the way up to 1 over n. And a useful fact to know about the nth harmonic number is it's about log n. Okay. And what this really means is that for any number of players n, there exists a fair cost sharing game for which the best Nash equilibrium has social cost that is h of n times that of the social cost of opt. Okay. So before we try to prove such a thing, are there questions about what the statement of the theorem means? Yeah. All of these, we'd love it if they were small. So like price of stability, price of anarchy, like ideally, if it was a just world, it would always be 1. Oh, because we want to understand exactly what it is. So I'm also going to prove a theorem upper bounding it. It's going to turn out to be exactly the nth harmonic number. So we're going to lower bound it and upper bound it, which is great from the perspective of us understanding it. We're going to know exactly what it is from the perspective of, like fairness and justice in the world. It kind of sucks because it's, like growing with n. It's not, it's not a great bound, but that's what it is. Yeah. Oh, it just means that I could go in to a partnership with you where we're going to build this length of fiber optic cable, and you pay 90% of it, and I pay 10% of it. The fair just means we split it evenly. Okay, so questions about what the theorem means? Okay, so remember what this theorem means. It just means for every n, there exists a fair cost sharing game for which the price of anarchy is, sorry, the price of stability is the nth harmonic number. So, in this direction, right, we're going to have to argue something more complicated when we upper bound the price of stability. But in this direction, really, we only need to give an example, right? You tell me n, I need to demonstrate to you the existence of a particular fair cost sharing game that has whose best equilibrium, ideally its only equilibrium is worse than opt by the factor that I claim. Okay, so proving this theorem will really be an exercise in giving a particular example. I'm going to write down on the board a particular cost sharing game that has this property, and that will prove the lower bound. Okay, because the statement of this theorem is an existential statement. There exists a game in which things can be this bad. Okay. Okay, so what does it look like? We need to, write down an n-player cost-sharing game. Here's what it looks like. Okay, so we're going to have n players, 1 through n, who each have some starting location. Okay, it's going to be one of these vertices. And they'd all like to build, a connection to the same destination up here, C. Okay. Now there's 2 ways they could do it. Each player could, on their own, just sort of buy a direct connection from their source to the destination. Okay, so there's the option for each of them to buy a direct connection. Or there's sort of this common meeting point down here. They could all send their traffic down here. And then if they did that, they have the opportunity to buy a shared connection that, this link they could buy that would, on which they could all share, and their traffic would all go along there. Okay, so what are the costs? Well, let's say that actually it's really easy to get to this shared meeting point. The costs for all of these links are actually 0. It's free. Okay, and this shared link here, they could purchase that for 1 plus epsilon dollars, where epsilon's just going to be some positive number that you should think of as really small. Going to make it as small as we want in this argument. Okay, so there's this piece of infrastructure that they could all share that costs 1 plus epsilon dollars, and if they bought that, then that would be it. They'd all be connected to their destination. Or they could buy these sort of individual links. How much do those cost? Well, player 1 could connect for $1, a little bit less than the shared link. Player 2 could connect for half a dollar. Player 3 could connect for a third of the dollar, so on and so forth. And player n could connect for 1 over n, fraction of a dollar. Okay, so this is the setup. Okay, so my first question is, what is opt? Suppose I could just tell people what to do to minimize social cost. What is the way to connect all n of these players to their destination so that the cumulative infrastructure costs are minimized? Yeah, they should all share this edge, right? If they all share this edge, the total infrastructure costs are just 1 plus epsilon. So something that I can make arbitrarily close to 1. Like there's clearly no way to do any better than that. Like if I don't buy this edge, even just connecting player 1 is going to cost 1, and connecting any one of the other players will get me above this budget. So like the optimal thing to do from a perspective of social cost is just to like all share this edge, and the total infrastructure costs are 1 plus epsilon, arbitrarily close to 1. But is this an equilibrium? No. How come?
Because the cost variable, well, that's what that's on X.
Yeah, like since this is a congestion game, you can think about equilibria through the lens of best response dynamics. No matter where we start, if we run best response dynamics, we're going to get to an equilibrium. Okay, so you can figure out what the only equilibrium is by just thinking about what happens if you start there and then start running best response dynamics. So what's going to happen? Well, players 1 through n-1 are going to be pretty happy with this solution, right? Like player 1 certainly wouldn't want to deviate. Like he's paying only 1 plus epsilon over n. His deviation would cost him 1. He doesn't want to deviate. Player 2 doesn't want to deviate. Player 3 doesn't want to deviate. But player n kind of wants to deviate, right? Because player n is currently paying his fair share of this edge, which is 1 plus epsilon over n. But he could just buy this direct connection, which it costs him only 1 over n, which is a little bit smaller, right? So if we started here, the nth player would have a best response to deviate to buying the direct connection. Now, once he did that, all of a sudden the n minus, now there would only be n-1 people sharing this connection. And so everyone would be paying 1 plus epsilon over n-1. And so now player n-1 would have a small incentive to deviate. Then there'd only be n-2 people sharing this connection. Then player n-2 would have a small incentive to deviate. And the whole thing would unravel until there are only 2 people sharing this connection, okay, paying 1 plus epsilon over 2, player 2 would now be better off buying the direct connection that costs 1/2. And now, if player 1 is choosing between paying 1 plus epsilon on his own and playing 1 on his own, he'd be better off playing 1. So like, although the optimal solution here involves everyone sharing this edge and has cost 1 plus epsilon, the only equilibrium in this game is for everyone to buy the direct connection. The only Nash equilibrium in this game has social cost, well, 1 plus 1/2 plus 1/3 plus 1 over n, which is the nth harmonic number around log n. Okay, so the price of stability in this game, right, is just the ratio between the nth harmonic number and opt. It's the ratio between h of n and 1 plus epsilon. And I can make epsilon as small as I want. So if you claimed for me that the price of stability for this class of games was anything that was smaller than the nth harmonic number, by making epsilon small enough, this would be a counterexample to that claim. Okay, so that claim is not true. So the price of stability is at least the nth harmonic number. Okay, makes sense. You look like you have a question.
That's really like also kind of a way you're saying to go about if you increase those numbers more, so it was like one. And like we'd be able to like backtrack.
That's right. So for this construction, you can't really modify it to get something better than the nth harmonic number. And in fact, the next claim is going to be that there is no other construction that does that either. So the next claim is going to be that actually the price of stability in this class of games is also at most the nth harmonic number. So it's like exactly equal to the nth harmonic number. And that this example is the absolute worst case. Yeah.
About if there's only one, what's the price of stability?
Yeah, so the price of stability always measures the best pure strategy Nash equilibrium. The price of anarchy always measures the worst. And if the game only has one pure strategy Nash equilibrium, like this one does, then in this particular instance of the game, the price of anarchy is equal to the price of stability. But like, that's not always the case. Sometimes there's more than one equilibrium.
He's one.
It's not one because we're still comparing to, like, we're not comparing the best Nash equilibrium. If we were comparing the best Nash equilibrium to the worst Nash equilibrium, then if there was only one Nash equilibrium, the quantity would always be one. But that's not what we're doing. We're comparing a Nash equilibrium to opt. So like in this game, for example, there is only one Nash equilibrium, but the price of stability is not one, it's about log n. Yeah. Yeah, so suppose you said, I don't believe this theorem, like this is bullshit. The price of stability is smaller than h of n. It's like h of n minus 1. Okay. Then I would say, okay, well, here's a counterexample to your claim, right? By making epsilon as small as I want, I can cause the price of stability in this game to get arbitrarily close to h of n. And so in particular, if you claimed it was anything strictly smaller than h of n, well, by making epsilon small enough, this would be a game in which the price of stability was bigger than what you said it was. Yeah, which would be a contradiction to any claim that the price of stability was anything strictly smaller than h of n. Okay. Okay. Right. So this was just an example. This is some particular class of games in which things can be as bad as h of n. You might wonder, like, if you're more clever, could you come up with an even worst case? Like maybe things could be worse than this. But the next claim is that they can't. This is the worst case, not even up to constant, up to like exactly the worst case, right? Like the claim is that in fair cost sharing games, the price of stability is never larger than h of n. Okay, and let's just make sure we understand what this means, right? Because again, we're talking about a class of games, right? So just as this theorem was really about an existential quantifier, like for every n, there exists a game where the price of stability is at least h of n. This is this theorem is really about a universal quantifier for every n, but for every fair cost sharing game with n players, the price of stability in that game is at most h of n. Okay, that's the claim. Right, so we've seen an example of a game where the price of stability can be as large as h of n. This theorem really says this game is the worst case. In every single fair cost sharing game you can show me, I can prove to you that the price of stability cannot be larger than h of n, which again is something on the order of log n. Okay, does the statement of the theorem make sense? And by the way, like, once you understand the statement of this theorem, the lower bound, like conceptually, the way you prove it is sort of straightforward. It was asserting the existence of some game with a bad price of stability. And so like the proof was always going to be an example. Like I would like construct a game for you, and we would just like work out in that game, what is the price of stability? Here, we're making a claim about all fair cost sharing games. We're saying, for every fair cost sharing game you can show me, right? So it doesn't matter how many facilities there are, it doesn't matter what these WJ facility costs are. For any fair cost sharing game, it doesn't matter what subset of the facilities are legal actions. Like for any fair cost sharing game you can show me, the price of stability is at most the nth harmonic number. Like here, I can't prove this by giving an example. So there's like a universal quantifier. So we're going to need to like understand something about the structure of such games so that we can prove this theorem. Yeah. That's right. So really what we showed is for any number less than h of n, for any number, like, I don't know, what's a good variable name? P, or V for value. For any value V less than h of n, there's a game that has price of stability greater than V. That's actually what we showed. But like in particular, that means the price of stability cannot be less than any such V. Yeah.
mapped onto this structure, this is like, and making that structure any more complicated inevitably increases the price of stability.
I guess it depends on what you mean by this structure. Like it has nothing to do with like this picture I drew on the board. A cost sharing game is a game of this form. To tell me, to describe a cost sharing game to me, you need to tell me how many facilities there are, what the action set is for each player. Each action set can be an arbitrary subset of the facilities, and what these numbers WJ are. That describes an instance of a fair cost sharing game. So it doesn't have to be played on a graph necessarily. Right, so in particular, like that, it has nothing to do with that picture I drew on the board, but it does have to have this form. Like when I say fair cost sharing game, I mean a game that can be written like this. You still look puzzled? Yeah. Okay. Good questions. Other questions? Okay, so is it clear sort of what we're claiming here? That for any fair cost sharing game, you can show me, again, specified by a number of players, a number of facilities, an action set for each player, which is just an action set for each player is just a collection of subsets of the facilities, and a sort of infrastructure cost WJ for each facility, right? That's what defines a fair cost sharing game. For any one of those, the price of stability is at most the nth harmonic number. Okay, so we need to like know something about these games. So let's remember what we know about these games. So, like these are congestion games, right? So everything we once knew about congestion games, like still true. And if we like think back hard, we still know it. So we really only ever knew one thing about congestion games, right? Like how did we argue that best response dynamics converges? Well, we figured out that congestion games were potential games. They were exact potential games. They had a potential function, and that potential function had the property that every time a player makes a best response move, the change in potential is exactly equal to the change in player's cost. And so in particular, if a player is only moving to decrease their cost, the potential function decreases. Okay, so we know that. And in particular, like it wasn't some abstract potential function, it was this potential function. So let's just like page that back into our memory. Right, this is just the potential function we used when we were studying best response dynamics in congestion games. The potential function, which just assigns a number to every game state, looked like this. We just summed over all of the facilities that had anyone playing on them. For each of those facilities, we summed from k equals 1 to the number of people playing on the facility. And what were we summing up? Well, it was just the cost of that facility when k people were on it. Okay? So this isn't exactly social welfare, but this was the potential function. Okay, so this is, okay, not new, like this is just, like we're remembering what we once knew long ago, beginning of this class. Okay, this function decreases when people play best response moves. Everyone, if not remember it, at least remember once having known this. Okay. So like in our case, like in general, we were used to thinking about this in some abstract way because we were talking about like arbitrary congestion games. We didn't know anything about the loss functions. But like in our case, since it's a fair cost sharing game, we know what the loss functions are. Like the loss function for facility J, when there's k people playing on it, always has this form. It's like the capital cost of building facility J divided by k, the number of people playing on it. Okay, so the potential function in our case is this. And, just like looking at this, this capital cost WJ, this is common to every term, right? Everyone's paying, WJ over k when there's k people on it. So we can pull this out, right? And we can write the potential function as just the sum over all of the facilities that has anyone playing on it, times the capital cost of that facility, WJ, times the sum from k equals 1 to the number of people playing on it, like 1 over k, right? That's just noticing that the cost function is WJ over k, WJ is common to all these terms, so I'll pull it out in front of the sum. Okay. And, like in the worst case, right, what is this? It's 1 plus 1/2 plus 1/3 plus 1/4 up until the number of people playing on it. In the worst case, all n people are playing on each facility, right? So upper bounding what this is, it's at most 1 plus 1/2 plus 1/3 plus 1/4 all the way up to 1 over n, which is exactly the nth harmonic number. Right, so I can upper bound this by the sum over all of the facilities that anyone's playing on of the capital cost of that facility times the nth harmonic number. And if you remember, like we sort of stared at the social cost objective, right? The social cost objective in fair cost sharing games is just the sum of the capital costs of all of the facilities that end up getting built. Okay, it's just like this term here without the h of n. Pretend the h of n is not being projected onto my hand. Okay, so like one observation that really just comes from like digging up from the depths of our long forgotten memory what the potential function is, and then just plugging in the specifics of this game. It's just that this potential function, it's not social cost, but it's not entirely unrelated to social cost either. It's upper bounded by social cost times the nth harmonic number. Okay, does that make sense? Okay. Okay, so the claim here is that the potential, it's no bigger than social cost times the nth harmonic number. But I also want to claim that it's only bigger than social cost. So I want to claim that, like this objective function, it's bigger than social cost. Okay, well, how do we know that? Well, let's just like look at the second line of this derivation, and there haven't been any inequalities yet. So this is exactly the potential function. It's the sum over all of the facilities that end up being built of the capital cost of that facility times this term. Now this term is at least 1, right? Because it's 1 plus 1/2 plus, we don't know how far it's going to go. It's going to end after the number of people playing on that facility. But the number of people playing on a facility that's built is at least 1. And so like whatever this term is that's multiplying the capital cost of facility J, it's a number that is 1 or larger. Okay. Now social cost is just the sum of the capital costs of the facilities that end up getting built. This thing is the sum of the capital costs of the facilities that end up being built, each times a multiplier that is 1 or larger. So the potential function, in addition to being upper bounded by social cost times h of n, is also lower bounded by social cost, right? So like this potential function, which, like confusingly for the early part of this class was not equal to social cost, in this class of games, okay, it's not equal to social cost, but it's not entirely unrelated. It's sort of sandwiched between social cost and social cost times the nth harmonic number, whatever it is that lives between these two bounds. Okay. Okay, and so now, like, it's always annoying when to prove a theorem, you need to like sit down and do calculations. Calculations are always ugly. It's much better if you can just like sit under a palm tree or something and conduct a thought experiment. So let's do that. Let's, like the rest of the argument will be proof by thought experiment. Okay. So our goal is to compute, we've got an arbitrary fair cost sharing game. We don't know what the game looks like. We just know it's a fair cost sharing game. Our goal is to somehow compare the social cost of the best Nash equilibrium to the social cost at opt. How are we going to do that? Well, we don't know much about this game, but like there's some game state that by definition achieves social cost opt. Let's give that a name. Let's call that A star. Okay. It would be great if A star was a Nash equilibrium already. Then the price of stability would be 1. But it might not be. So let's imagine what happens if we start play. Like we're gonna like the thought experiment is going to imagine what happens if we run best response dynamics. best response dynamics starting where? Well, let's start best response dynamics at A star, this game state that achieves social cost equal to opt, which is fine, right? Like the way we analyze best response dynamics, it sort of really didn't care where we started. So let's start at opt, why not? And to start running best response dynamics. And we know that no matter where we started best response dynamics, it will eventually converge. It'll converge to some pure strategy Nash equilibrium. Okay, so we started at opt, so we turned the crank, we ran best response dynamics, it ran, and eventually it stopped at some pure strategy Nash equilibrium, call it A prime. We don't know which pure strategy Nash equilibrium this was. Maybe it was the best one, maybe it was the worst one, but at least it wasn't any better than the best one. Can't be better than the best one. Okay, so let's think about what is the social cost at A prime. Okay, and we'll be pessimistic and we'll sort of assume that this was the best Nash equilibrium. If there's a better one, even better. Okay, so what do we know? Well, we know that the social cost at this Nash equilibrium is upper bounded by the potential function value at this equilibrium. That's just because we observed up here that the social cost at any game state is upper bounded by its potential function value. Okay, so the social cost at this equilibrium A prime is at most the potential function value at A prime. Now the potential function value at A prime is at most the potential function value at A star, the starting point. Why? Yeah, I mean, it was because we got to A prime by starting at A star and running best response dynamics. And the whole point of a potential function is that it only decreases when we run best response dynamics. Right, so we started at A star, we turned the crank on best response dynamics and ended at A prime, and the potential function decreased at every turn of that crank. So the potential function at the Nash equilibrium is only smaller than the potential function at opt. But the potential function at opt is at most the social cost at opt times h of n because of the other relationship we observed between our potential function and social cost. And the objective function at A star is opt because that was how we picked A star. A star was the game state that had objective function opt. And that's it, right? Like the social cost at the equilibrium we ended up at is at most h of n times opt, and we don't even know if the equilibrium we ended up at was the best one. If there's a better one, it's even smaller than this. Okay, so this means no matter what game you give me, through this thought experiment, I know that the social cost at the best equilibrium in your game is at most h of n times opt. Okay, in particular, you can't come up with a worse example than this. Like if you think about this game, like we even went through this thought experiment sort of explicitly. We started at opt, we thought about what would happen if you ran best response dynamics and you ended up at the Nash equilibrium. Yeah. Yep. There can't be a Nash equilibrium that has social cost better than A star. There could be one that has better than A prime though. A prime is not necessarily the best Nash equilibrium, it's just the one we ended up at. But in the worst case, there's not, because we have seen an example where this h of n bound is actually tight. Good, makes sense? Okay, proof by thought experiment. Okay. So that was the price of stability. Let's just tie up some loose ends and establish what the price of anarchy is. The price of anarchy in these games is much easier to establish and much less interesting and much worse. So the first claim is that in fair cost sharing games, the price of anarchy could be, for the price of stability, it was always at most log n, the nth harmonic number. The price of anarchy could be terrible. It could be as large as n. Okay, So the claim here, right, remember how what these claims mean, right? When, the claim here is really for any n, for any number of players, there exists a fair cost sharing game for which the price of anarchy is as large as n. So I just need to give you an example to prove this. And the example is very easy. Suppose we've got n players starting at S, and they would all like to go to T, and there's two choices for how to get there. Okay, they could all share this path, or there's two choices how to get there. They could split them up however they like. This path has capital cost n. This path has capital cost 1. Okay. If you could tell them what to do, what would you tell them to do? Should they build the expensive link or the cheap link? Probably build the cheap link, share the 1. Right, so they could all share this 1. Okay, can't do better than that, opt is 1. But if they all share the n link, that's also a Nash equilibrium, because if they're all sharing the n link, each of them is paying only 1. And so none of them has any incentive to unilaterally deviate to the cheap link, because if they did that, they'd have to pay the capital cost for it all on their own, which wouldn't be any cheaper than what they're currently paying. And if you wanted to make it a strict preference, you could make the 1 a 1 plus epsilon. Okay, so opt is 1, but there exists a Nash, right? The worst Nash is n. Right, so all sharing 1, by the way, is also a Nash equilibrium. Right, so in this particular game instance, the price of stability is 1. The optimal solution is a Nash equilibrium, but there's another Nash equilibrium, and that one's bad. That one's as bad as n times worse than opt. Okay, so if we're looking at prices, so in these fair cost sharing games, even though in like our price of stability example, there was a unique Nash equilibrium, like there are games with multiple Nash equilibria, and the worst one can be way worse than the best one. Okay, so the price of anarchy in these games can be as large as n. And this is the worst case. Like the price of anarchy is also at most n. So in particular, it's like exactly n. And just to sort of say out loud the quantifiers again, what this means is that for every fair cost sharing game you give me, right, it doesn't matter how you instantiate the capital costs, the action sets, the number of facilities, whatever. For every fair cost sharing game you give me, the price of anarchy in that game is at most n. So in particular, like this parallel edges example is like the worst one. Okay. Actually, we're going to prove something a little bit stronger than that, right? So what is the statement here? It's saying, if I look at social cost, the sum of the cost functions for all of the players, that social cost in Nash equilibrium can be at most n times the social cost in the optimal solution. But what we're going to establish is something even a little bit stronger than that. We're going to establish that player by player, if A is a Nash equilibrium, their individual cost at the Nash equilibrium is at most n times their individual cost at the optimal solution. And so, of course, if that's true, then it's also true that the sum of their costs at equilibrium is at most the sum of their costs at the optimal solution. But what we're actually going to prove is the slightly stronger statement that this is true player by player. Okay, makes sense. Okay, and this is pretty straightforward. So what do we know about the worst Nash equilibrium? We don't know much about it, but like we do know it's a Nash equilibrium. So let's use that. Right, like what does it mean that something's a Nash equilibrium? It means that no player can benefit, no player can decrease their cost by unilaterally deviating from their part of the equilibrium to anything else. So we know that any deviation by any player starting from a Nash equilibrium will only increase the cost. So we can think about any deviation we want. Let's think about this particular deviation, the deviation in which player I switches to playing the action that they would have been told to play in the socially optimal solution. So there's this like, socially optimal solution A star. Let's think about what happens if player I deviates from playing their part of the Nash equilibrium to their part of the optimal solution, so AI star. Okay, because A is a Nash equilibrium, we know that this deviation cannot be beneficial to them. Okay, now what is their cost if they play their part of the optimal solution, but everyone else plays, nobody else deviates, everyone else plays their part of the Nash equilibrium A? Well, it's the sum over all of the facilities that they're playing in the optimal solution. But the load on that facility isn't what it is in the optimal solution. The load on that facility is at least, the load on that facility in A, or at least one if nobody's playing on it in A, because now player I is playing on it. Okay, so it's the sum over all of the facilities that player I plays on in the optimal solution, but the load on those facilities isn't what it is in the optimal solution. It's the load on those facilities given the number of players playing on it in this Nash equilibrium A. Now, what is that? Well, like the load on the facility is just the capital cost of the facility divided by the number of players playing on it. Now, in the worst case, player I finds himself playing alone on each of these facilities. Okay, that's right, because the cost decreases the more players are playing on it. So the most expensive each facility could be is the full capital cost of that facility. That's like the, that's the cost that player I would experience if he had to purchase that facility all on his own. So player I's cost is upper bounded by the sum of the costs of the facilities, the sum of the capital costs of the facilities on all of the facilities he would have played on in the optimal solution. Okay, or equivalently, I can write that as n times the sum of the capital costs of the facilities he plays on in the optimal solution divided by n. I'm allowed to multiply by n as long as I divide by n. And this is the best case cost for the facility, right? Like the cheap, if I'm going to play on some facility J, like the cheapest I could ever possibly experience it at is if I was sharing it with absolutely everybody else. So in particular, this is at most n times my cost in the optimal solution. Right? Like here we're saying, well, like in the worst case, if I deviate to my action profile in the optimal solution, I have to pay for the capital cost of the facility all on my own. And in opt, maybe I got to split it n ways, but it can't be worse than that. Okay. And that's it, right? That establishes that for every player I, my cost in the Nash equilibrium is at most n times my cost in the optimal solution. And so in particular, if I sum up the costs of all of the players at the Nash equilibrium, it's at most n times the sum of the cost of all of the players in the optimal solution. And so this really is the worst case example. There could be game states where the social cost was worse than n times opt, but those game states could not be Nash equilibria, right? Like, no matter what fair cost sharing game you give me, the worst case cost for any Nash equilibrium, remember our first inequality here was using the Nash equilibrium condition, the worst case cost in a Nash equilibrium cannot be worse than n times opt. And so once again, this is the worst case example. So the price of anarchy in this class of games, it's exactly n. The price of stability in this class of games, it's exactly the nth harmonic number, which is about log n. Okay. So that's it. Let me know if you've got any questions. Otherwise, see you next class.